Hey everybody, welcome back. Mr. Smith here. What I'm going to do today is walk you through all the solutions for A22. There's going to be a lot of teaching that goes on in this video. Also, if you want to, just go ahead and scroll right to the end of the video and you can look at me panning and I'll show you the solutions, and if you just want to check your answers, you can do that. First thing, what you're going to be asked to do in all the worksheets we do for this big chunk in our module is to write a velocity time graph that captures the motion. This one's easy. McLaren F1 accelerates from 0 to 45 meters per second. This is the graph of a car speeding up. So I've got velocity, I've got time, and I've got a car that goes from 0. Why the graph? It helps you organize the information. So especially for hard problems, the graph is really handy. So I'm going to expect you to do it. Next thing you're going to do is you're going to write down a list. So LEPS means list, equation, plug in and solve. So you start with V1, V2, D, A, and T. And the thing about physics is when we get into more complicated problems, there's a lot of ways that we can write these problems depending on the info they give you that can make them really hard to solve. So you being organized is crucial. So here's a little bit of an easy one. Velocity 1, 0 meters per second. Velocity 2, 45 meters per second. What I'm going to ask you to do, or at least what I do, is to figure out change in velocity and average velocity right away at the beginning of the problem, because you almost always use them. So first things first, over here I'll take V average is going to be V1 plus V2 divided by 2, and I go ahead and work that thing through and I figure out for these numbers I get 22.5 meters per second. Now if you do it this way, that's showing enough work, so I'll be okay with this. Make your list, write down the formula, and show me how you got the average velocity. That's an easy enough calculation that I trust you're going to get it right. You don't have to write these in. Next thing, change in velocity is V2 minus V1. And if I do the V2 minus V1 over here, I get 45 meters per second. And you'll take a little more space and you'll be a little neater than I just did, where you won't mash the graph into the work. But anyway, I've got my two things, delta V and V average. So what they want me to do is figure out A, the acceleration of the car, and I'll just do that right here. Acceleration equals change in V over change in T. Since I already figured out what the change in V is, that's pretty easy for me. So I'm going to take 45 meters per second and divide that by the time, so 6 seconds. And when we do the work, we figure out that the McLaren accelerates at 7.5 meters per second. Okay, so we got that. You can pencil that into the list. And then finally, in part B, they're going to ask us for the distance. So the distance the car is going to travel is going to be D equals V average times T. Now, I could get this thing from the area under the triangle. That's a really good method to use. What I'm going to do is show you the formula way to do it. So D equals V average times T. I'm just going to take the 22.5 meters per second that I figured out a second ago and plug that in there times my 6 seconds, and I calculate that the car is going to travel 134 meters as it speeds up. Okay, so those are all three phases. You've got the graph, you've got the two equations, and we're going to go through and do some more repetitions and show you how they work. Okay, second one. Very similar to the first one. So click on the video if you want to. It's pretty hilarious. But this is, as you'll see from the video, this is basically a go-kart with a Type R Honda engine in it. So it's really a fast little car. And if I pencil in the numbers and use my graph, in 2.9 seconds, the car goes from 0 to 26.8 meters per second. And I can do the same thing I did with my list. So V1, V2, D, A, and T. So V1 is 0. V2, 26.8 meters per second. Didn't give us the other ones, but they did give us the time. You might wonder, in questions where they give you the time, those are a lot easier than if they don't give you the time. All right, so let's just jump right in. If I were to go and get the V average of these two, I can just add them up and divide by 2, and I get 13.4 meters per second. Again, I trust you to figure that out. If I were to go and get the delta V, I take V2, subtract V1, and that's going to give me 26.8 meters per second. Okay, moving on. If they ask us for A and B, the acceleration is just going to be delta V over delta T. So I write out the formula, write down the equation, plug in and solve. So 26.8 meters per second over 2.9. And this might be a little quicker even than the McLaren F1. And yeah, it is. It's 9.24 meters per second per second. You could also write that as meters per second squared. This is getting up into the range of super quick motorcycles, which is almost what this is. It's like a flat motorcycle. Anyway, B, get the distance. D equals V average times T. Got it? Got the V average, 13.4 meters per second. I'm leaving the labels on stuff. And this is what your work should look like. 2.9 seconds, easy to follow. And you're really telling people one step at a time what is going on. So this number right here is absurd. In less than about 40 yards, maybe a little more than 40 yards, this car goes from 0 to highway speed. So that's nuts. Okay, anyway, 2 down, a couple more to go. In this one, a ball is thrown in the air at 30 meters per second. 3.06 seconds later, the ball is stopped. So not all the graphs are the same. Think about that and put that information onto a graph. Here, the ball is going fast, and then later it slows down and stops. So what I want to do is make basically a car slowing down graph. Now, a couple things. The motion here is up and down, but that doesn't make any difference. Really, a ball throwing up in the air and slowing down is exactly the same thing if you twist it sideways as a car driving forward and hitting the brakes. Both of them are just an object slowing down. The big thing you're going to get from your graph, though, is you're going to be thinking when you make out your list, V1, V2, D, A, and T. The V1 here is a bigger number than the V2. This one's 30 meters per second, and the V2 is going to be 0. The D, we don't know it yet. A, we don't know it yet, but they did give us the time, which is nice. So this is going to be a pretty easy one for us. And what I'm going to do is just go ahead like I have been and get the V average. So V1 plus V2 over 2 is 15 meters per second. Now, right here what I've got, you've got to use your common sense. You can't be a robot. You've really got to think. Change in velocity is V2 minus V1. So it's 0 minus 30. Also, when you think about change in velocity, this is not a ball that gained velocity. This is a ball that lost velocity because it was slowing down. So both of those things, the formula, delta V is V2 minus V1, and the change in velocity is minus 30, they mean exactly the same thing. Okay, and that's going to make a difference to me when I come down here and I go and figure out the acceleration. So we're going to get A. Yeah, A is to find the acceleration. So A is change in V over change in T. So I've written out my formula. And we're just going to plug in. Delta V was minus 30 meters per second. Whole thing took 3.06 seconds. Go ahead and put that stuff in, and you get negative 9.8 meters per second and that's a fun fact. The planet that we live on has some really strong gravity. We've never been to another planet, at least I haven't been. I don't know about you, but the gravity on this planet is really strong. And it's interesting that just dropping a ball or throwing a ball up in the air and watching it slow down is quicker than almost every car that you will ever drive. So B, is going to figure out we did compare the two. This thing's quicker than even the Ariel Atom. It's quicker than the McLaren F1. Kawasaki Ninja, those things are actually a little quicker than gravity, which is interesting. So anyway, finally, let's go ahead and get the distance. D equals V average times T. And we'll plug in. V average was 15 meters per second, and the time it took was 3.06 seconds. And we'll go and figure it out. The answer turns out to be, let's go get it. Right, and that turns out to be 45.9 meters, okay? And that's going to be the height of the ball. Okay, almost out of the woods. What we're going to do is talk again about something speeding up or something slowing down. It's an acceleration problem, but let's read it. A car accelerates uniformly from rest to a speed of 30 meters per second in a time of 5 seconds, period. The car then crashes into a barrier stopping in a time of 1/2 of a second. And here's where velocity graphs really earn their money. You can make a realistic scale picture out of that. So I'm drawing a car speeding up graph. So this right here is 30 meters per second. And then I have a car slowing down graph, but you notice the slope of the graph is the acceleration of the car. So if I drop a little line right here, this is 5 seconds that it takes the car to speed up, and this is out here is going to be 5.5 seconds. This is really 2 problems for the price of 1. So what I've got here is the total distance traveled by the car, the total accelerations as it speeds up, accelerations as it slows down. It might be easier to do this one just by looking at the graph. That's my opinion. When you have questions that involve more than one part, I really like to go after them by using some graphing skills. So what graphing skills would I use? Total distance. Total distance would be the total area. And so what I'm going to do is just get the area of this first shape, and that's going to be area 1. And we'll get the area of the second shape, which is also a triangle, and area 2. And so let's go right down here and get after area 1. So area 1, 1/2 base times height. The base is 5 seconds. The height is 30 meters per second. Go ahead and plug those 2 things in, and you get 75 meters. Alrighty. Over here, let's go ahead and switch colors maybe. I'll leave it as blue. Notability is going to fight with me if I do that right now. So we'll go ahead and get this area out here. Area 2 is 1/2 base times height. Why? Because it's a triangle. So the base, 0.5 seconds wide times 30 meters per second. And I go ahead and pull the trigger on that. Looks like 1/2 of 15 is 7.5 meters. And add the 2 of those things up, and the answer to A, the total area, is the total displacement of the car. Looks like 82.5. There you go. Okay. Now, B and C, pretty easy to figure out if you just use your graphing skills. So B, what's the acceleration of the car as it speeds up? It's going to be the slope of this line. So acceleration equals the slope of the line, and that's rise over run. Rise is the same thing we've been talking about. It's V2 minus V1. V2 is 30 meters per second. The car had 0 velocity in the beginning, so the rise is 30 meters per second. Over the run was 5 seconds, so the acceleration of this car was 6 meters per second, which is still pretty quick for a realistic car. Then slowing down, cars will accelerate a lot harder typically when they slow down than when they speed up, especially if you crash them. So rise over run here, do the same thing, except the rise is going to be minus 30 meters per second, and the run is going to be 0.5 seconds, and I'm going to get that the acceleration of this car is negative 60 meters per second. So what do you learn from that? A negative acceleration will fight a positive velocity. And that's why this velocity line came down so hard, because the acceleration was negative and it was a big number. Okay? Now, the last question. There's a lot to this one, and we're going to take you through it step by step. So the last question, it's a typical type of a problem that you're going to see a lot of times. So I'll set it up for you first. Driver of Porsche 944 is driving down a country road, crests a hill and sees a moose 40 meters ahead of him. The maximum acceleration that the car and brakes and tires can supply is minus 8.5 meters per second. Can he avoid a crash or not? Okay, this is what I call the does he hit the moose question. And it applies to a lot of different kinds you're going to see as we go forward. So does he hit the moose? Let's first of all get our velocity time graph. I've got a car that's moving fast, and it's going to try to stop. And so I'm going to have a velocity time graph that's going to look like all of my slowing down graphs. Okay? Here's the thing. This right here is the initial speed. It's 27 meters per second. And notice they don't give us the time. The time's a mystery. That automatically makes this a harder question. The second thing that they do is they ask us a critical thinking question. Can he avoid the crash or not? That's what makes this question special. So what I'm going to do is I'm just going to write down what I know. So V1, V2, D, A, T, and we'll go to town, and I'll show you what's what. Velocity number 1, 27 meters per second. Yep. Velocity 2, let's assume that this man does not crash. We're going to assume that he doesn't crash, because if he does crash, he probably is going to be not traveling 0 meters per second. So if I assume he doesn't crash, he may or may not travel 40 meters. So here's my advice. If you identify a does he crash question, take the distance and save it. Just leave it. Trust me on it and leave it. The acceleration is negative 8.5 meters per second. Watch what we do with it. First thing we're going to do is we're going to, as we have been, figure out the V average. So I just add these two up and divide by 2. I get 13.5 meters per second. And get the delta V. The delta V is going to be negative 27 meters per second. Okay, so we've got those two nailed down. What equations can I do? We will talk about the layer cake of physics formulas in class. What I want you to do is think about what formulas you have. Right now you've got 2 of them. You've got acceleration equals change in V over change in T, and you've got D equals V average times T. So I know the delta V, I don't know the delta T, but I do know the A. So I've got 2 out of these 3 things. That's a good sign. That's probably the formula I'm going to want to use. Here, just to compare, I pretended that I didn't have the 40, so I'm going to stand by my guns there. I'm going to pretend I don't know the D, I do have the V average, and I don't have the T. So that says to me that I shouldn't use this formula first. Okay? Watch what happens. I'm going to go along and use the acceleration formula, and we're going to work with that. So what I'm going to do first is go ahead and solve this first formula for delta T. So cross multiply the delta T, and then divide both sides by A. So if I take delta V divided by A, I'll get the time it takes the car to slow down. So what's the delta V? Negative 27 meters per second over the acceleration of the car, negative 8.5 meters per second. And what I find out is that the car takes, yep, got it, 3.2 seconds to stop. Now that I've got that, I can go now and figure out the distance. I'm doing this based on all numbers that say the car stops nice and smoothly and evenly. So let's go and see if this is true, and then we'll know the answer to the question. So D equals V average times T, and I go ahead and plug in V average 13.5 meters per second, and time is 3.2 seconds. And I go ahead and multiply those two things together, and I get 43.2 meters. And here's the critical thinking piece. 40 meters would have been wrong if I had used it, because 40 meters is really the whole point of the question. Does he stop in 40 meters or doesn't he? The moose is just standing there 40 meters away. And I know if the car travels 43.2 meters, then he traveled a little farther than the distance he had. So in real life, he does hit the moose. He did take a little bit too long to stop. But the good news is that the area of this triangle right here, 43.2 meters, is not that far off from 40 meters. So probably when he hit the moose, it's somewhere in here, and his velocity wasn't super high. Okay, there's a lot going on with that. So anyway, what I'm going to do is ask you to just take a quick look at your answers. We're going to scroll back to the top for those guys that are checking answers. There's 1. There's 2. Stop the video if you want to and compare. There's 3. There's 4. And here's the does he hit the moose question. Okay, so I'll give you a lot there. There's a lot of step-by-step. There's a lot of teaching that goes on. And bring some questions. I'll expect to talk to you soon. Take care, and thanks for watching. Bye-bye.